This is going to be case study 2 for control theory. So just a brief overview of what we're going to go over is going to be a project exploring the analysis of an automated steering control system. There's going to be two different cases that we're going to go into depth into. The first one's going to be an ideal system controlling the steering, and the second one's going to be a case with an accelerometer's feedback. So the first is case A. The GC of S is going to be the K constant. We're going to derive that later in the video. GA of S is going to be S, and this is going to equal B, and then the B was actually going to be your birth month, and my birth month is going to be 8 for me. And then GP of S is just our function that we got here for this, and it's going to be a unity feedback system. So the objectives, we're going to be going over the damping ratio and undamped natural frequency as a function of K, the lane change response of the system for different values of K, graph the position over time, or position versus time. I'm going to select appropriate control system parameters and determine the proportional gain for the controller to meet those specifications, and then I'm going to explain the reasoning behind my choice of K and the corresponding performance characteristics and any trade-offs made. So selecting the gain and explaining the choice. The system order. This is what I'm going to go over in the next couple slides. This is going to be a system order. Why undamped and not overdamped, critically damped, or undamped. The rise time, settling time, peak time, overshoot, and what's appropriate for lane changing. And then I'm going to go over the stability. So first I'm going to go through the block diagram math. In this system, I did GC of S times GA of S times GP of S, all with a unity feedback. And that was just the top right here, and then I had to incorporate the unity feedback right here, so it was going to be GC, GA, GP, divided by 1 plus GC, GA, GP. Once I worked that all out and I simplified it down, I got this equation right here, and I plugged in my 8, and I got this equation. So from that equation, I was able to derive the omega n value to be the square root of 0.8k, along with the dampening ratio value, which is going to be 0.5 divided by the omega n value. And that came from this equation right here. The top is going to be omega n squared, and then the bottom was going to be this middle value is omega n squared times zeta times 1/2. So that's how I derived those two equations. And then the lane change response of the system, graph versus position versus time. These are the different numbers that I used. One, I was going to go with that is just way too high. It gets a very nice response, and I get up there very quickly. I change lanes very quickly, but then when I'm coming back down, I get all the way up here, then I'm like swerving back, crossing back, and then it levels down. The 0.8 was just going to, in my books, take a little bit too long. I could have used this number right here, but I decided not to. The whole goal is just to cross the 1 and then get back to that spot in a fairly quick, not so abrupt manner. So I decided to end up using the 0.9 as my K value, which I get up there fairly quickly, and then there's not a whole lot of like swerving back to get back down here. And the 0.5 is going to be a bad example, and that was just going to be a overdamped system, an overdamped system. And that's just a bad example because you go up and you're just taking way too long. It takes about 8 seconds to change lanes. That's just not a good example. And the system order for this one is going to be second order because that's the highest order in the denominator of the S values. And then why underdamped, not these other ones. The overdamped would have taken way too long to change lanes, as I talked about earlier. Critically damped would take too long, but it was a little quicker, so it would be okay, but still not a great idea. And then the undamped, you would never end up getting into a lane. You would just keep crossing back and forth, or even end up in the ditch, or crossing into something. That's a really bad idea. You don't want to be doing that, putting yourself in harm's way, or putting other people in harm's way. And the rise time, settling time, peak time, overshoot, and what's appropriate for changing lanes. I thought that the rise time getting in across to this lane in about 2.1 seconds was pretty good. the peak time you're finally in that is like the farthest across the lane in about 4.5 seconds is pretty good. And settling, I mean, there's going to be always some little bit of steering back and forth to get perfectly straight, but all things considered, 7 seconds to change lanes and be perfectly still in that lane is a pretty good idea for it to be. Then the overshoot was 10%. Stability for this first case, this is what I got for the 2 complex pulls, and this is going to mean it is going to be an undamped system, underdamped system, sorry. And then going on to case B, this is going to be the system. So to solve for this one, I had to do GC times GA times GP. I had to connect or combine these two in series down here, so 1 over S squared times H of S. Then I'd have to use the unity feedback, and I'd get all of this times, or all of this divided by 1 plus all of this times all of this. And then I'd have just one feedback block, and I'd have to do all of this once it was combined at times 1 over S squared to get this all simplified down. So it was just R of S, G of S is a whole block right here, and X of S is the output. These are the different variables that you see up here. And then in my code, I used GT of S as the 1 over S squared value because it's both the same. So I'm going to be going over basically the same objectives and review as I went over in the first system. Case B block diagram math was going to be what I just talked about, and this is what I ended up using. I used MATLAB to simplify it down for me because I wasn't going to go through every single step and make a silly little math error and then put it into MATLAB and have the wrong numbers because I messed up on my own. This is just what I talked about earlier and what it all was going to be coming out to. The GT of S is the 1 over S squared. Lane change response for the system A and B, graph versus position versus time. This is going to be case A's getting up there, but it's going to be a little bit slower than case B, which you can see here. It gets up there a little bit quicker. It wasn't much of a difference in this system. If I would have gotten bigger numbers and bigger numbers, it probably would have been more significant, but in this case, it's not really that significant, but it's a better, quicker way to get there, as we'll see in a little bit. And then stability, just going over this. These are my poles. And then since these ones right here are about a factor of 10 almost away from these ones, this is going to be an undamped system, and we're going to be able to say that this is going to be a second order system approximation, sorry, due to the complex pairs being way too far apart. This helps to justify that. And these are basically the same things that I mentioned earlier. Nothing changed in these. There's still a reason we're using the underdamped, neither of the others. And then just comparing these, the case B was getting up there just fairly slightly quicker, and it also settles slightly quicker, and its peak time is slightly quicker, as you can see through these. And then the overshoot is a little bit higher. It's just helping the lane correct, which is why these numbers are a little bit lower. And that is my presentation. Thank you.